We now turn our attention to a special case which involves a combination of translational and rotational motion, and it's called pure rolling. What's pure rolling? Well, suppose when you drive your car, the tire moves forward, but under normal driving circumstances, there is no slipping between the contact point, between the tire and the ground. So the contact point A between the tire and the ground, which is point A, is momentarily at rest, right? The entire tire is rotating about this point. This point does not slide forward or backward. This is the case of pure rolling, or rolling without slipping. When I say slipping, I mean the contact point between the rolling object and the ground. Let's look at some special features of pure rolling. Suppose the object of circular cross-section at one moment is at this position, and let me use a certain color to denote a line connecting the center of the object and the contact point with the ground. Let's use a blue line. Okay, so let's actually mark this line blue so that you can see how it moves. A little time later, the object rolls to a new position, which is here. So, the new contact point with the ground is now what we call A prime. Okay, so A prime is here. What happened to this blue line? Well, the blue line connects the contact point of the ground with the center of rolling, and the contact point is no longer A, it's A prime. So this blue line has turned like this. Okay, this is the new center, right? The blue line has now moved like this. If you look at the new reference line, vertical line, between the contact point, new contact point A prime, and the new center, there is an angle theta. Okay, so we say, as far as rotation is concerned, this object has rotated through an angle theta. Meanwhile, what happens translationally? Well, translationally, the center of the object is moved from O to O prime by this much. Okay, by this much. How far is this? Well, it's the same as that distance, right? It's the same as that distance. But that distance is the same as this distance, this length of this arc. In fact, this is the original point A, which made contact with the ground at t equal to 0. Okay? As you rotate forward like this, A is lifted off the ground, and eventually A prime now touches the ground. So the arc length covered is equal to the distance between A and A prime. If the radius is r, then how long is this arc length between A and A prime? The arc length is equal to r times theta, right? But that equals the distance between r and r prime, which is also the distance covered by the center of the body from here to there. Let's call it x. So r times theta equals x. X is how far the center moves translationally, and theta is the angle of turning. So this formula relates translational motion with rotational motion in the pure rolling. This makes sense because in the pure rolling, the reason why the center of the object can move from place to place is only because the object rolls. So if it rolls by twice as much angle, of course, the center is going to move forward by twice as much. There is no slipping going on. If there were slipping going on, then the whole thing can slide forward or backward, in which case you can have extra x without rotating any further. So then you will lose the proportionality between angle rotation and the translational motion. But that is not the case here. We have twice as much the angle turned, resulting in twice as much translational motion. Okay, suppose I take a time derivative of both sides. Remember, x is the distance between the center and the perimeter. It's just the radius. It does not, so r does not change. Okay, x is the distance moved, and theta, of course, also changes. So when I take a derivative, r does not change, and if I have r d theta dt equals dx dt. What is d theta dt? Isn't that omega, right? The angular speed. What about dx dt? That is the speed at which the center of the object moves. So therefore, we conclude that for pure rolling, v at the center, VO, equals omega times r. This is a condition necessary to sustain pure rolling. The angular speed and the speed of the center of the circular object must be related, like VO equals omega times r. Now, in the pure rolling, this is point A, the contact point. Every point on that object in pure rolling is momentarily doing a circular motion about point A with various radius. For example, this point at the tip, okay, this point at the tip does a circular motion like this. It has twice the distance to point A compared with that point, which is at the center. Okay, so if you look at the linear speed of this point versus the linear speed at that point, they're related. How are they related? Well, for this linear speed, we have omega times r, r is the radius. For that one, we got omega times 2r, right? This is 2r. So you see, they have different linear speed depending on how far they are from point A. But they have the same angular speed if this whole thing is a rigid body. Now, here is how this green point moves. In fact, the green point also does a circular motion about point A. This is the radius. What about that blue point? Well, that blue point also does a circular motion. Here is the radius of the circular motion. It does this. Okay, it moves like this, 90 degrees, 90 degrees. And of course, the red point moves forward with this radius, radius also in circular motion. And the black point, of course, moves with twice the radius. So this is what happens to every point engaged in an object of pure rolling. Only this point A, the contact point, is momentarily at rest. Everything else is doing a circular motion of various radius. So they may have different linear speed, but they got to have the same angular speed, omega. This is the kinematics of pure rolling. And now let's apply the torque theorem as well as Newton's second law for the center of mass to study the dynamics of pure rolling. One of the most important examples of pure rolling is an object of circular cross-section rolling down an incline without any slipping. You know, this can be a sphere, whether solid or hollow. It can be a cylinder. It can be a hollow ring. Anything that has circular cross-section. It rolls down without slipping. Okay, be careful. It does not slide. Let's see what happens. What I want to know is I want to figure out, let's say, for example, as the thing goes from the top of an incline to the bottom, by the time it reaches the bottom, how fast is it rolling? Or how fast is the center of mass moving? For simplicity, let's say it's a uniform object so that the center of mass is also the geometrical center right here at the center of rotation, at the center of the circle. And the point A, the contact point between the incline and the object, that is the axis, that is the location of the axis of rotation. The whole thing is rotating about an axis passing through point A. Okay, let us study the angular acceleration. If I know the angular acceleration, I can figure out how fast it moves by the time it reaches the end. To do so, just like we did before, we need to study both the rotational and translational motion of this object, because after all, it's doing both in pure rolling, both translational and rotational motion. Let us draw a free body diagram first. Okay, for this object, you got mg, right? You got mg. And you also have normal force N. Is that all? Well, if these were the only two forces, in which there's no friction, let's say for simplicity we start from rest. Okay, we start from rest. So the things start to go downwards, right? How is it going to go downwards? Look, there's no friction. And we only got these two forces. Both of these forces pass through the center of mass right here. Okay, so if I apply the torque theorem about the center of mass, which of course I can always do because it's the center of mass, this guy has no torque, neither does mg. So the net torque is 0, which means alpha is equal to 0, which means it is not going to change its rotational speed. But it does not rotate to begin with, right? We start from rest. So alpha is 0 and omega initial is equal to 0, which means it will not roll at all. What happens is that it's simply just going to slide down without any rolling. Obviously, that is not what we want. So how do you start a rotational motion from rest? You must have some non-zero alpha, which means a non-zero torque. So who is providing the torque? Not N, not mg. So what do you think? Well, think about it. In a real incline, you always have some friction, right? At the contact point A, the tendency of this object is to slide downwards. And friction is against that, so automatically you are going to get a friction. Friction. This friction, as you see, about to the center of mass, this friction encourages a clockwise acceleration, angular acceleration. So you're going to roll faster and faster and faster. This is the friction that provides the angular acceleration in relationship to keep up with linear acceleration of the center of mass. Okay, the question is this static friction or is this kinetic friction? Well, it depends on whether this point slides or not. If this point does not slide, okay, it only has a tendency to slide, but there is no sliding going on here, then, of course, by definition, it is the static friction I'm dealing with. Now, when it comes to static friction, immediately you know one thing. I do not know the exact value of static friction. All I know is that static friction can range all the way from 0 up to a maximum value, which is equal to mu s times n. Has it reached mu s times n? I don't know. Okay, it may not be the case. So in general, we just can write it down as Fs. Make sure, though, Fs does not exceed mu s times n. All right. As a matter of fact, you can imagine if the angle is very small. If the angle is very small, it does not roll down very fast. Right? So you have a small linear acceleration and correspondingly a small angular acceleration. A small angular acceleration requires a small torque, which means Fs required to sustain pure rolling is actually pretty small. Right? This is what causes pure rolling. It's pretty small, and therefore it may not have reached its maximum value of mu s times n. Okay, imagine I gradually raise this angle theta. You know, obviously it's going to slide down faster. Okay, that's, I mean, as far as the translational motion, it's going to have a greater acceleration down the slope. And in order to keep up with it, remember alpha has to relate to ACM. Alpha equals ACM over R for pure rolling, just like omega equals VCM over R. Therefore, you need a greater alpha, which means a greater torque, and the lever arm is always the same, right? It's always the radius. And therefore, Fs has to increase. Fs has to increase. At some point, Fs may have reached the critical value of mu s times n. That means you're using 100% of the available static friction to provide enough torque to sustain pure rolling, to keep up with linear acceleration of the center of mass. What's going on at this point? We say at this point the angle of inclination has reached a critical value. You can still have pure rolling, but barely. Okay? If the angle is is steeper than that, then you would require even greater Fs in order to sustain pure rolling, to provide the torque necessary for the angular acceleration to keep up with linear acceleration. And Fs cannot do that anymore. It has already reached its maximum value. So when the angle is greater than that critical angle, what happens? Well, you can have sliding going on. Okay, so you cannot make it too steep. Common sense, right? If it's too steep, you're not going to sustain pure rolling. It's going to slide. It's not pure rolling anymore. But assuming that, for our case, it is pure rolling, in other words, the angle is lower than the critical angle, can I find the angular acceleration and linear acceleration for the center of mass? Okay, to do so requires some knowledge of Fs. I have to know what Fs is. Unless, of course, I can eliminate Fs from my calculation, from my equation. And how do you do that? Fs is not 0. But what's the trick? Well, the trick we learned is that if I choose point A as my observation point to apply the torque theorem, then even though Fs is not equal to 0, the torque it provides about point A is 0 because there's no lever arm, right? So obviously it is a good idea for me to choose point A to apply the torque theorem. That way I don't have to deal with the torque of Fs. That torque theorem will tell me what alpha is. Okay, so this is the best approach we can think of if you just want to know what alpha is. As a matter of fact, take that point to the observation point, point A. Okay, n, just like Fs, passes through that point A. Therefore, neither n nor Fs provide any torque. The only thing providing torque is mg, and that's a clockwise torque. What is the lever arm? The lever arm, by definition, is the distance, vertical distance from point A to the line of action of mg. So if this radius is r, this will be lever arm is r times sine theta, right? So multiply this by mg, I get a torque. Torque about point A is mg times the lever arm, which is r sine theta. What is that equal to? I at point A times alpha. Okay, this immediately tells me what alpha is. Isn't that great? In fact, let me write down alpha. Alpha is mg r sine theta over IA. By the way, IA is the rotational moment of inertia about this axis going through point A. I can write it in terms of ICM if I want to. It's ICM plus md squared. Remember the parallel axis theorem? D is equal to the radius r. So I can write this as ICM plus mr squared. That's alpha. Once I know alpha, can I find ACM? Yes, ACM, that is the angular linear acceleration of the center of mass, is related to the angular acceleration, alpha, with ACM equals alpha r. Okay, ACM equals alpha r. So it is simply equal to mg r squared sine theta divided by ICM plus mr squared. There we go. I get ACM. Now, once you get ACM, if you want to, you can also find that Fs. Because now, if you apply the Newton's second law for the center of mass translational motion, then along the incline, I got only two forces. One is mg sine theta going down, the other is Fs going up, right? The net force along the incline should provide the acceleration of the center of mass along that direction, and the center of mass only accelerates along that direction, parallel to the incline. So, if I apply Newton's second law, along the incline, I have mg sine theta going down minus Fs going up equals mass times ACM. I know what ACM is. It's right here. That tells me what Fs is. Okay? Now, with that knowledge of Fs, can you find the critical angle at which you get barely able to hold on to pure rolling, and above that angle, pure rolling will give way to sliding? Yes, you can, because you can solve for Fs now, right? You want to make sure that Fs is equal or less than mu s times n. That's all. So that's the inequality which will give you the critical angle. What's n, by the way? Well, simple. Fs is along the incline, so it doesn't change anything in the direction perpendicular to the incline. Perpendicular to the incline, the net force has to equal to 0 because the center of mass does not move up and down along the perpendicular direction to the incline. So I still have n equals mg cosine theta. Okay, mg cosine theta is the component perpendicular to the incline going down, and n is the other force going up. So I still have n equals mg cosine theta. Okay, so again, you can solve for Fs and make sure Fs is less or equal to mu s times n. That will give you the critical angle. So I'm going to leave that to you. Okay, what I want to do is I want to take a closer look at ACM. Okay, take a closer look at ACM. Let me divide both the numerator and denominator of a term by mr squared. Okay, if I did so, I get this result. ACM equals to, divide everything by mr squared. Okay, g sine theta, mr squared and another mr squared. So 1 here, I'm going to do this term first, plus, okay, ICM over mr squared. This, of course, is less than g sine theta. All right? Less than g sine theta, because the denominator is greater than 1. What is g sine theta exactly? Do you recall one of the sample problems we did for chapter 5? Okay, you have a box sliding without any friction down the incline. What was the acceleration of the center of mass? That was g sine theta, wasn't it? G sine theta, because mg sine theta is the only force pulling it down. And let it equal to ma, you get a equals g sine theta. Right? Now it's less than g sine theta. Why is that? Because there's a friction pulling it up, which cancels with part of the mg sine theta. That's why it's less than g sine theta. So that makes perfect sense. Okay, this would be equal to g sine theta only if, in fact, less or equal. It equals to g sine theta only if this term is equal to 0. So ICM is equal to 0. When ICM equals 0, that means this thing has no rotational inertia, which means you don't need a friction force at all to cause rotation. Rotation can be caused without any torque because you don't have to pay a price. I is equal to 0. That is the only case where ACM equals G sin theta, because you do not need a friction to sustain pure rolling. Okay, so physically what's going on is that as the thing rolls without slipping, it requires an upward static friction to provide the necessary torque to accelerate the angular motion so that alpha can keep up with ACM. Okay, that is from the dynamical point of view. In order to sustain pure rolling, you need a backward Fs, which is contradicting to the gravitational force pulling it down. We are going to look at this problem from two different angles. It's a good problem, so I want to study it from all angles. That is, we are going to, first of all, we're going to look at the rotation from the center of mass point of view. Okay, not from point A point of view. I'm going to rewrite torque theorem about the center of mass. See if we get the same result. Okay, and secondly, we're going to look at the same problem from energy consideration. So